Hey y'all, we're just gonna do a quick review of the Test 1 practice exam before the review session on Friday. So if you just have a specific question or if you can't come to the review session, you can just watch this video. So we're gonna get right into it. The first thing you have to do, and you're gonna have to do this on your exam too, is download the R data file and import it into R. So this is slightly different than the import data set. What you're going to do is hit download and it'll show up in your downloads. And in your R, you'll file, and click on that that's in your downloads. And then tell R, yes, I want it to go into the environment. And all of this data shows up in your global environment. This is all the data you're going to need for the entire exam. Was all just put in to your R. So that's all you have to do. And then first question, put in your seat number. That will be just for the exam. Number 2, Amazon tracks the following variables for pants that are sold on the site, which customizes the inseam length to match the exact dimensions of the purchaser. Which variables are quantitative? So we have to check which variables are quantitative, which means we can apply mathematical functions to them. So that includes inseam length, colors not quantitative, styles not quantitative, number of pockets is quantitative, and brand is not. The other 3 are categorical, inseam length, and number of pockets. We can do the mean of them, we can do the standard deviation of them, we can do mathematical functions on them. So that is why those 2 are quantitative. Number 3. So this question is talking about a telephone survey about risk factors in health populations. And they basically ask about diet, weekly physical activity, HIV/AIDS status, tobacco use, and level of healthcare coverage. And it says this data is in CDC, which is in our global environment. The variable health plan indicates whether the respondent had some form of health coverage or did not. So 1 means yes, they had health coverage, 0 means they didn't. And then it says the smoke 100 variable indicates whether the respondent had smoked at least 100 cigarettes in their life or did not. Same thing, 1 means yes, 0 means not. So we have to select the true statement. So in looking at this, we're comparing 2 different variables and seeing if there's an interaction between them. So what we're going to do is do a mosaic plot of health plan versus smoke so we can visualize the difference between people who have smoked and people who have not, comparing their health coverage. You could do this with just a regular table, but it's way easier to visualize it if you have it in a plot. So I'm going to make my R a little bit bigger, and we're going to do table of health plan and smoke 100, okay? If you don't have table in this, you're going to get an error, and you're going to be like, that's not a mosaic plot. So if you get a bunch of 1s and 0s, remember you have to have table in your mosaic plot function. And you don't have to add this part. It's totally not necessary, but it makes it super easy to understand because the first thing you put in is going to be on the x-axis. The second thing you put in is going to be on the y-axis. So without this, it's kind of confusing to look at the mosaic plot. So let's run this. And we see health plan is on the x-axis, because it's the first thing I put in, and smoking is on the y-axis. I put those labels in right here. So now let's look at the answer choices. You can hit on R to pull this up. So we're comparing respondents who smoked at least 100 cigarettes versus ones that have not smoked 100 cigarettes. So we're comparing this smokers to non-smokers. And we're comparing their health coverage. So smokers, about probably 90% have a health plan, 10% don't have a health plan. And then looking at people who have not smoked, which is this whole section, the same thing, about 90% have a health plan, about 10% don't have a health plan. So we are going to say respondents who have smoked at least 100 cigarettes are about as likely to have health coverage as those who have not smoked that much. So this means smoking and health plan, whether you've smoked or not, health plan is pretty independent of whether you have smoked or not. Question 4. The contingency table shows the number of people in a company categorized by their gender and promotion success in a given year. You know there are 180 women in this company, and promotion, success, and gender are independent. So this is the key word that is needed to be able to answer this question. So if promotion and gender are independent, we know the percentage of men that get promoted is going to be the same as the percentage of women that get promoted. So I'm going to calculate the percentage of men that get promoted, which is 160 divided by the total number of men. And you get 44.444. So I'm going to call that 160 over 360. So I know 44.4% are promoted. So there's 180 total women. What's 44.4% of 180? And I get 80. So that means 80 women are promoted in this company during this year. Because of the independence, the percentage of promotions are the same. Question 5. An optometry shop collects data on its customers. The data is in vision and summarized below. What is the conditional distribution of eye condition for females? So we're looking at conditional distribution, which means we're looking at the females row. So I only care about this conditional distribution of the females row. If we were looking at a marginal distribution, we would be looking at something in the margins. But we're looking at conditional, so it's this data, this 4, 16, 12, and 32. So the percentage of females that are nearsighted is going to be 4 divided by the total for females, which is 32. So I'm just going to run that one, and I get 0.125, so I know immediately that it has to be this last option. But I can check the rest to make sure I'm right. 16 divided by 32 is going to be 0.5, which is right here, and 12 divided by 32, the percentage of females that need bifocals, is 37.5. So just remember, conditional distributions, we're dealing with the data in the middle of the table. Marginal, we're dealing with the data in the margins. Number 6. The dataset runners contains information about 40 students that ran a mile-long race. The data indicates the school that each student attended, whether they finished the race within 8 minutes or not, and the height of the runner in inches. Out of the Macomb students, what is the percentage of students who finished the race within 8 minutes? So, what I'm going to do is look at a data table of runners comparing the school they attended. I'm looking at Macomb's versus the percent of students that did the 8-minute mile. So I'm going to run this, and I see, okay, so Cockrell, 11 students didn't do it, 5 did. Macomb's, 8 students didn't do it, 16 did. So, what is the percentage of students in Macomb's who finished the race within 8 minutes? So I'm looking at all Macomb students, which is 8 and 16, 8 plus 16, and the percentage who finished the race, which is 16. So I got 16 divided by 16 plus 8, which is going to give me 67%. And out of the students who finished the race in 8 minutes, so we're looking at all of the students that were yes, which is the 16. What is the percentage who were Macomb students? That's going to be 16 divided by this column total, which is 76%. So little bit more advanced in getting R to do things for you. We can add margins to the table, so you don't have to do that addition. All I did was have the same line as line 22, except I add margins on the outside of it. So the only difference for this is that the sums, the totals, are already on the outside for you. So instead of adding 16 plus 8 to get the total, it's already here for you, it's 24. You can just do 16 divided by 24 to get this same 67%. 16 divided by 21 for this column, the same 76%. Either way, you get the exact same answer, whatever you're more comfortable with. Question 7. The table below belongs to a survey that is about one's gender and favorite way to eat ice cream. If a male survey participant is selected at random, what is the probability that his favorite way to eat ice cream is not from a cup? So, what we need to do for this question is to see the percentage of males that are anything other than eating ice cream from a cup. So what I'm going to do first is add up the total number of males that were surveyed. And I call it total male. And you can see in your values, my total male value is 1,200. So 1,200 males were surveyed. And then I want everything other than cup. So I'm going to do this total, that 1,200 that we just added together, minus 592, divided by the total. So I'm getting the percentage of everything that is not cup. I run this, and we get 50.67. So you can write it as 0.5067. You can write it as 0.507. Pretty sure these require 3 decimal places at least. So if you 3, it'd be 0.507. Your Canvas exams will also accept if you put 50.667. They accept both. I would write it as a decimal though. Question number 8. This table represents the first 8 observations from a sample of 200 individuals who reported their age, race, income, and job satisfaction score on a scale from 0 to 100. The income distribution could appropriately be displayed with a blank. So we're going to check all that apply. So income here, these are the options: less than 10,000, 20,000 to 23,000, more than 100,000. So one that we can eliminate right away with income is a time series plot. It will not be a time series plot because there's no element of time to income. So now we're down to bar chart, histogram, and box plot. So remember the difference between a histogram, a bar chart, and a box plot is histograms and box plots are used for quantitative data. Bar charts are used for categorical data. And then the question is this income categorical or quantitative? And the answer is it's categorical because these are not numbers, they're categories. So this would be a bar chart. If the income had instead have been, type in your exact income like $9,000, $22,000, $115,000, then you could use a histogram or a box plot. But because these choices are these categories, these ranges, we have to use a bar chart. Question 9. This is another question about that telephone survey. So it's asking us the best way to visualize the relationship between gender and weight. So we're dealing with gender, which is a categorical variable, and weight, which is a quantitative variable. and we're comparing two things. So we want something that can have room for a categorical variable and a quantitative, and it lets us compare two things. So a box plot lets us show the quantitative variable of weight, but there's no way to show the categorical of gender. Bar charts are harder to compare gender versus weight. It is possible to make one bar chart of weight, average weight, and one bar of average weight for females and one bar of average weight for males. But that's harder to compare. And the histogram, there's no element of comparison in there. So the best option for this is side-by-side box plots compared to bar charts, because side-by-side box plots, they'll let us see the range of the weight for each gender, the median of the weight for each gender, and the spread, the Q1 to Q3 for each gender. So side-by-side box plots are the best way to visualize the relationship, the differences between gender and weight. Question 10. The dataset runners contains information about 40 students that ran a mile-long race. The data indicates the school that they attended, whether they finished the race within 8 minutes or not, and the height of the runner in inches. It says if the 76-inch tall student is removed from the data, the mean would blank and the standard deviation would blank. So we can think about this in our minds conceptually about what would happen, and we can actually do the calculation. So I'm going to show you both. So let's look at this runner's data. And I'm going to click here twice to sort the height largest to smallest. And it says, and we see the 76-inch tall student is the highest one. It's the max of this data. It's the tallest student. So we're trying to see if the mean of the height, what the mean of the height would do if we remove this entry. So think about it. If I remove a super high outlier, then my mean is going to decrease because the high outlier is removed. The mean isn't being pulled up by the high outlier anymore. The standard deviation would also decrease because I don't have a high outlier anymore. The outlier is removed from the data. So if you don't understand how removing that top outlier affects the spread or the mean, we're going to do it by math in R to see the differences. So first I'm just going to do a mean of runners, $ height, the data, $ the column name. I get 64.475. Then I'm going to do standard deviation, which is SD. I get 3.17. So now this is how I'm going to remove that height. I'm going to say runners, and these brackets are about when we're talking about some sort of row or column in the data, okay? So inside these brackets, we always put row, comma, column. Always row, comma, column. So what I'm saying is go to runners, row 10, column 4, make it NA. So what this is doing is going to runners, row number 10, column number 4, which is height, and make it NA. So let me run this statement. And it just did that. So now let's go back to runners and let's go to row 10. Go back to row 10. And we see the height is NA. That's exactly what we wanted it to do. So now I'm going to do the mean and the standard deviation again, but I have this other thing, which means we don't care about the NAs. If I don't have this NA.RM equals true, it's going to give you an error. It's going to say NA. So we have to tell our NA.remove, remove the NAs, is true. Remove the NAs, we don't care about them. Do the mean, and I get 64.179, which has decreased. I remove the high outlier, so the mean decreased. And then we'll do standard deviation. We don't care about the NAs. Remove them. 0.59, which is less than the original standard deviation of 3.17. Question 11. You're managing a local store in Houston. You present your sales summary to a potential investor. You would like to present what your weekly revenue looks like in a typical week in 2017, but you don't want your numbers to be affected by the drop in sales due to Harvey. Which summary statistic should you use? So we want to show what a typical week is like. So we're not trying to measure the spread of the data, really. We're trying to get an average of the data. We're trying to get something about describing the center of the data rather than the spread. So variance describes the spread of the data. Standard deviation describes the spread of the data. And IQR describes the spread of the data. So we're not really worried about the spread of the data here. We're worried about the typical average week. So then we have to choose between mean and median. And we don't want something to be affected by the outliers of Harvey. So we know median is not affected by outliers, but mean is. So that's why median is the best choice for a measure of the center of the data. Question 12. This is another one about that telephone survey. So it says heights are given in inches. What is the interquartile range of the adult heights included in the sample? So there are two functions we can use to get our numbers, Q1 and Q3. We can use summary of the data, $ height, and it gives us all of these numbers, or you can use something called 5num of CDC $ height. You get the exact same numbers. This one has the mean, this one doesn't. The summary ones are labeled, the 5num ones are not. So whichever one you like more, use that. But we know Q3 is 70, which is the fourth number in this one. Q1 is 64, which is the number in this one, and the second number in this one. So the IQR is just Q3 minus Q1, which equals 6. In a data set of fish weights at an aquarium, the z-score of the weights of each fish is calculated. Which of the following must be true? So this first one says, z-scores are calculated by subtracting the mean and dividing by the standard deviation. That's right, that's just the definition of z-scores. They're calculated by subtracting the mean and dividing by the standard deviation. The second one, all z-scores must be positive. That is not true. When we think about our distribution, a normal distribution, if the weight of a fish is exactly the same as a mean, then I'm doing the weight minus the mean divided by the standard deviation. And if the weight is the exact same, then I'm going to have a z-score of 0. If I have a weight that is less than the mean, I'm going to have, example, the mean is 4, and the value that I got was 3. My value was 3, and the standard deviation is 1/2. So if I have my value minus the mean divided by the standard deviation, I get -2. That just proved any value that's less than the mean is going to have a negative z-score. So this is not true. The z-score of a fish that is 2 standard deviations heavier than the mean would be 2. That's right. The z-score basically means the amount of standard deviations away from the mean. So if something is 2 standard deviations above the mean, then it's going to have a z-score of 2. This fourth one we already talked about. The mean has a z-score of 0. So mean minus mean divided by standard deviation, we get 0. And the last one, all the z-scores must range between -1 and +1. This one is super easy to get confused with correlation, with R, the correlation coefficient. They're not the same thing. Remember, we just proved that value minus mean divided by standard deviation had a z-score of -2. So there's no way that all z-scores must range between -1 and +1. Which of the following is or are true about the standard deviation? Check all that apply. So a standard deviation is the measure of spread. It's one of the measures of spread we can have. And let's talk about each one of these. Is it possible to have a negative standard deviation? We cannot have a negative amount of spread, so it's not possible to have a negative standard deviation. However, it is possible to have a standard deviation of 0. If the points are not spread out at all, if all of the points are the same, if we all had 4.0 GPAs, then there would be a standard deviation of 0 for GPA. There's no spread in it. It's all the same. This third one, I have said a lot, the standard deviation is a measure of spread. It is not a measure of center. Center, about the center of the data, that's things like mean, median, and mode. Things that are measures of spread are standard deviation, IQR, variance. Question number 15. Make a histogram of the data in dataset. Which of the following are true about this distribution? So we're just going to make a histogram, which is the function, and we're going to do dataset, which is the name of the data. And then we have to do $sign the column called data. So I'm going to do that. I can make this a little bit bigger. And we're saying, is it symmetric? Is it left skewed? Is it unimodal? Is it bimodal? So something cannot be both symmetric and skewed. We have to pick one or the other. Something cannot be both unimodal and bimodal. We have to pick one or the other. So is this symmetric or left skewed? It looks pretty symmetric to me. It looks basically identical on each side. So this is symmetric. And then, is it unimodal or bimodal? Is there one hump, or is there a hump and then a gap and then another hump? And this is bimodal because there's this gap in the middle of these two peaks. Question number 16. If the correlation between x and y is -0.5, then when x decreases, y will do something, and a regression predicting y from x will account for something of the variance of y. So we're talking about R, that correlation coefficient. So if the correlation coefficient is negative, that means there's an inverse relationship. So when x decreases, we think y is going to increase. It's not always increase, because think about the plots. If I were to do a scatter plot of this, it's not going to be a perfect straight line. If the correlation was perfectly 1.0, then it would always increase. But because it is 0.5, it's just going to tend to, but not always increase. This is because of the inverse relationship, and the correlation is not that strong. A regression predicting y from x will account for blank percent of the variance of y. So this question is asking about r squared, which is the percentage of variation in y accounted for by x. The percentage of variation in y accounted for by x. And how do we figure out r squared? We just square the correlation coefficient, which is -0.5 squared, which is 0.25. So that's 20%. So that gives us less than 50% of the variance of y. Number 17. An analyst runs a regression to predict the stock price of Apple based on the stock price of Google and finds this regression equation. If the price of Google increases by $10, then how much do you expect the price of Apple to change? Enter a positive number for an increase and a negative number for a decrease. So the change in the price of Apple based on the price of Google is just the slope. And we know the slope is 0.88. So you can just do 0.88 times the amount of increase, which is 10, to get 8.8. And if that doesn't make sense to you, we're going to try it a different way. So let's say the price of Google is $1. So original price is $1. So what will the price of Apple be? So Apple 1 is going to equal 0.23 plus 0.88 times 1. That's going to be the original price. So Apple 1, that's the first price. Apple 2 is this new price after the price of Google has increased. So that's 0.23, which is the intercept, plus 0.88 times 11, because the price has increased by $10. Now, I want to see the difference. So let me do Apple 1 minus Apple 2. Apple 2 minus Apple 1, and I get 8.8. So you can do it either way. You can plug test numbers in and find the difference, or you can just look at the slope. Number 18. The Economic Research and Information Center collects cost of living information for the 50 states relative to the U.S. average. The cost of living file gives the cost of living index for different expenses. If you predict the housing index from the grocery index, which regression assumption will be violated? Okay, so let's look at the cost of living data. So we're trying to predict housing index from grocery index. So first thing to check, quantitative variables condition. Are these indexes quantitative variables? Yeah, they are. They look like quantitative variables. I can take the mean of them. I can take the standard deviation of them. So we can eliminate quantitative variables. They are quantitative variables. That's not violated. Now let's look at linearity. So we're going to see if this grocery versus housing indexes, if that looks pretty linear. So let me just plot them. I'm going to do plot, data name, $ my x, comma, data name, $ my y. So let me plot these. It shows up in this picture right here. And there might be a little bit of a curve down here, but this data looks pretty linear to me. We can put a straight line through this. If something is obviously linear, it's going to violate the linearity, but this looks pretty linear to me. So we can eliminate the linearity condition. It passes linearity. Equal spread condition. So this is the thing. This is the condition where we look at the residuals. We need to plot my x values versus my residuals. So to do that, I need to make a model first. So I'm going to do a model with my LM function, my linear model function, of my my y variable, and then this squiggly sign, which is above the tab. If you don't know where it is, it's above the tab on your keyboard. And your data $, your x. So I'm going to make a model of that. It made that model for me. And then I want to plot the x values versus the residuals. So I want my x values on the x-axis, so I put those first. And then my y, I want the residuals of whatever my model is called. I'm going to plot this. And I see that these residuals get super, super spread out as the cost of living grocery index increases. So basically what this means, as I'm fitting a model to this data, it's not as good at predicting the higher grocery numbers. It's worse at predicting them. So this fan basically shows that this regression model isn't good because this data fans out. It's not good at predicting the higher numbers. And then the success-failure condition is not a regression assumption. So don't even worry about that. That's for binomial. Equal spread is violated because of this x values versus residuals looking like a fan. Question number 19. Laptop sales now represent more than half the computer sales in the US. Campus Computers at UT sells both types of computers, and in the last year sold 66% laptops and 34% desktops. Reliability rates for the two types of machines are quite different. In the first year, 6% of desktops require service, while 17% of laptops require service. What is the fraction of all computers sold that were both laptops and need service? So this is just a probability rule. You just need to write them down in your cheat sheet and remember them and use them. So the probability of laptop and need service is the same as probability of laptop times the probability of needing service, given that it is a laptop. From this question, 66% are laptops, so this is the probability of selling a laptop. And the probability of a laptop needing service is 17%. So I want 66%, which is 66% of computers sold were laptops. 17% of laptops sold need service. I just multiply those together, and I get 0.112. So 11% of all computers sold were both laptops and needed service. Question 20. A sample of 1778 homes in Austin last year produced the data in the table for the number of bedrooms and house price. Is the price of the house independent of whether it has 3 or more bedrooms? So independence means the change in one does not affect the other. So this means a house that's less than $300,000 is the same probability of having 3 bedrooms as a house that's $450,000 to $600,000. So let's check. Let's see the percentage of homes that have 3 bedrooms if it's less than $300,000. So 333 homes that are less than $300,000 have 3 bedrooms out of the total amount, which is 333 plus 498. That's about 40%. Now let's check the 300 to 450,000. That's different. Only 36% of houses have at least 3 bedrooms. Then we check the last one, 450 to 600,000. 133 divided by the total. And I get 31%. So an even smaller percentage of homes have at least 3 bedrooms at this higher cost. So we know they're not independent. The price does affect the percentage. And now we're down to the first choice and the third choice. And more expensive houses are less likely to have 3 bedrooms because this percentage was decreasing. 30% have 3 bedrooms compared to 30%. Question 21. 200 people, 60% have black hair and 30% have green eyes. If 20 people have both black hair and green eyes, how many people have black hair or green eyes? So that question a little while ago was an and question. This is an or question. So we just remember our probability rules. And this is probability of B or G is going to equal probability of B plus probability of G minus the probability of B and G. So this probability of having black hair and green eyes is going to be these 20 people out of the 200. So that is 20 divided by 200, which means 10% have black hair and green eyes. So we have to subtract that out so we don't double count people. So the probability of having black hair is 0.6, plus the probability of having green eyes is 0.3, minus 0.1, which is to not double count people, and we get 0.8. Be very careful about what the question is asking you. It's asking how many people have black hair or green eyes, not the percentage, how many. So I have to take this 80% and multiply by the total number of people to get 160. Be very, very careful about what the question is asking you, because I would have missed that too. I would have just put in 0.8. Always go back to the question. Question number 22. A data analyst is analyzed an interesting relationship between total sales and region of the country. She fits a regression to this data and finds this equation. Can she use this equation to predict sales in region 7? So you've probably never seen a plot like this, and it's because a condition is violated, and you should never fit a plot like this because region is not a quantitative variable. I know they're numbers, but they are categorical. Region is categorical. I cannot take the average of region. So it violates the quantitative variable criterion. We would never fit a regression model on region versus total sales because region is not a quantitative variable. Last question, number 23. Dr. M teaches 2 sections of stats, one section at 8 a.m. and another section at noon. He gave both classes the same exam and then wondered whether the later section did any better than the earlier section. The grades for each section are in the grades file, and we're trying to examine the distributions. So there are a lot of different ways to do this question. I'm going to show you what I think is the easiest way to do it and the best way to visualize the data, but if you ask your professor, if you ask your friends, there are a lot of different ways to do the same exact question. So let's look at the grades, and we see a bunch of names, a bunch of scores, and some with noon classes, some with 8 a.m. So the best way for me to visualize the differences in distribution is going to be a side-by-side box plot. So in order to do the side-by-side box plot, I'm going to split this grades data up into the noon class and the 8 a.m. class. So this is just one way to do it. You don't have to do this. I'm going to make a subset of this grades data. So I'm telling R, take this grades data and only take part of it out, and I'm going to call it noon. And this is my condition. For something to be taken out of grades and put in noon, the class time has to equal, which is just an equivalency operator in R. Okay, so you have to have the equal, noon, in quotes. So it says pull everything out where class time equals noon. I'm going to run that, and I get another data in my global environment, and it's called noon, so I can click on it and make sure I did it right. All of these say noon, perfect. Do the same thing, and I'm going to call it 8. I'm going to make a subset of grades where the class time column is going to equal 8 a.m. I'm going to run that, and I see I get something called 8 in there. And all of these have 8 a.m. Perfect. So then I'm going to do a box plot of the 8 a.m. class score, the noon class score, and this part right here is not necessary for the side-by-side box plot. This is just for me to make it pretty and make it easier to understand. So let's run this. And this name, this extra parameter, what it did was call this one 8 and this one noon. Let me delete it and show you. Without it, it called them 1 and 2. The first one you type in here is the first one in the plot. The second one you type in is the second one in the plot. But I like to have the names, so you can do that if you want. So I have a box plot of the 8 a.m. class and a box plot of the noon. So let's go back to the question. And let's look at this box plot. So the median is that black line. And it's about 20 for the noon class, and it's about maybe 20.5 or 20.4 for the 8 a.m. class. So they did about the same on average. That's a less than 1 point difference. So they did about the same on average. So I'm going to cross out this one. The later class on average did not do better. It actually did slightly worse. Okay, so let's see, were they similar in spread? Was one more spread out? Look at this box is both the IQR is bigger and the entire range of the data is bigger. So the noon class data was more spread out. So the later class did about the same on average as the early class, but their grades were more spread out because the box plot is more spread out. You could also answer this question with a histogram. You could do the min and the max of each one and just look at the numbers. There are lots of different ways to do this question. And that's it for the practice exam. And if you have any other questions, email the TAs, come to the R help session, come to the practice midterm review in the mod lab on Friday, and we would love to help you. So good luck on your exams. Let us know if you have any questions.